Welcome back. In Part 2, we explored types of precipitation and their impact on flight. Now in Part 3, we'll dive into cloud evolution, embedded thunderstorms, and how to interpret weather charts to anticipate risks hidden inside the clouds. Let's begin with cloud development stages. Not all clouds stay the same. Cumulus clouds can evolve into towering cumulus, and then into full cumulonimbus, the thunderstorm cloud. This process depends on three ingredients: moisture, instability, lifting mechanism. When all three are present, the atmosphere becomes unstable, and vertical development kicks in. There are three main thunderstorm stages. Cumulus stage, updrafts dominate. Mature stage, updrafts plus downdrafts, precipitation begins. Dissipating stage, downdrafts dominate, storm weakens. The mature stage is the most hazardous, bringing turbulence, hail, lightning, wind shear, and heavy rain. Avoid it by at least 20 nautical miles, especially on the downwind side where outflows extend further. Now let's talk about embedded thunderstorms, CBS, hidden within layers of stratiform cloud. These are especially dangerous because you can't see them visually. You might fly into one without realizing it. Embedded CBS often occur inside altostratus or nimbostratus during frontal activity. On radar, they appear as strong echoes within a broad area of precipitation. Avoid flying through solid cloud layers without a full weather picture. Let's connect this to frontal systems. Warm fronts bring layered clouds that deepen slowly, cirrus, altostratus, nimbostratus. Cold fronts bring towering cumulus and CBS rapidly. Occluded fronts combine both, often producing embedded cells and complex layering. You can spot a warm front approaching by rising cirrus followed by lowering stratus. If rain begins and you're still far from the low-pressure center, it's likely a warm front. In contrast, a sudden drop in temperature and wind shift followed by showery precipitation suggests a cold front. These often bring short, intense convective cells, which can evolve into embedded CBS within broader cloud decks. Now let's talk about TROWALs, troughs of warm air aloft. These occur in occlusions, where warm air is lifted over colder air, forming cloud shields with embedded CBS. They're common in complex mid-latitude cyclones. TROWALs are marked on upper-level charts and can signal long-lasting, messy weather with multiple cloud layers and turbulent pockets. Avoid them on cross-country flights whenever possible. Speaking of charts, let's shift to SIGWX charts. These show forecast significant weather features including jet streams, CBS, turbulence zones, icing levels. They help you visualize which clouds are benign and which carry real risk. CB symbols on SIGWX charts are usually paired with altitude markers, e.g. CBFL 37500, and descriptors like EMBD, embedded, FRQ, frequent, or OCNL, occasional. Take these seriously, they reflect conditions reported or modeled across wide areas. For more detail, pilots use METARs, TAFs, and GAIRMETS to track cloud development and precipitation type. Pay special attention to CB in remarks. TSRA, thunderstorms plus rain. VCTS, thunderstorms in vicinity, all signal convective activity is nearby or building. Now let's review cloud cover terminology again. Few equals 1 to 2 octas. SCT equals 3 to 4 octas. BKN equals 5 to 7 octas. OVC equals 8 octas. When BKN or OVC layers involve CBS, it means the sky is mostly or fully filled with storm-capable clouds. Let's look at a sample METAR. This tells us thunderstorms and rain. Broken clouds at 2,000 feet with CBS. Overcast at 5,000 feet. Gusty winds. Plan for turbulence, possible wind shear, and a dynamic final approach. Now, let's look at how sounding charts help. A sounding shows a vertical profile of temperature, dew point, and wind with altitude. You can spot inversions, moist layers, and instability, helping you anticipate cloud types and icing potential. For instance, if temperature drops rapidly with height and the dew point is close to the temp line, expect clouds and possibly convective development. If the lapse rate is stable, stratiform clouds are more likely. Soundings also help spot icing layers. A moist layer at -5 degrees Celsius with no inversion? That's a risk zone. Use this info to plan climb descent levels and brief passengers and crew accordingly. Now let's talk turbulence in clouds. Stratus, usually smooth. Altostratus, light chop possible. Cumulus, light to moderate bumps. CBS, severe turbulence. Avoid the more vertical the cloud, the rougher the ride. The taller the cloud, the stronger the updrafts and downdrafts. Pilots must monitor ride reports, radar, and visual cues like cloud tops. Bright white, cauliflower-like towers equals growing cumulus. Stay away, especially near the top of the troposphere where instability peaks. CBS can generate outflow boundaries, miniature cold fronts that trigger new convection. These can form under cloud decks or beyond radar range. They show up as gusty wind shifts and sudden precipitation bursts. This brings us to multilayered clouds. You might fly through broken cumulus at 6,000 feet, then enter altostratus at 12,000, and finally hit cirrus at cruise. Each layer could affect aircraft handling, icing, or turbulence differently. Always check vertical layering during flight planning. If alternates are limited, avoid areas with widespread BKN plus CB layers. That combo limits escape routes and may restrict climb or descent options during emergencies. Let's finish with some real-world pilot tips. Always ask for PIREPs before departure into marginal weather. Use radar and satellite overlays together. Avoid cloud buildups with strong vertical texture. Cross-check temp and dew point on climb for icing risk. Brief alternates early if CBS are near your destination. Let's recap. Clouds evolve from cumulus to CBS through instability. Embedded CBS are dangerous and often hidden in layered systems. SIGWX, soundings, and METARs reveal what you can't always see. Turbulence, icing, and visibility all change depending on cloud structure. The better you understand cloud dynamics, the better you'll manage in flight. In the next episode, we'll conclude the Cloud and Precipitation series with Part 4, examining frontal cloud systems, visibility reduction, and techniques for navigating through complex skies. See you in Meteorology number 30, Clouds and Precipitation, Part 4.